Leibniz was a 17th century polymath. He is responsible for a lot of developments in physics. You might remember him from calculus, but it turns out he's also hugely influential in functional programming. And that's because Leibniz was really interested in the search for a formal language to describe mathematics. And that search was later picked up on by a whole bunch of other mathematicians, by Bertrand Russell and Whitehead, which was later picked up on by Alonzo Church and Turing. And they went on to develop the foundations of functional programming, lambda calculus, which we all use today when we code. Another thing which we can credit Leibniz for, which I only found out yesterday. In fact, he's the first person to write down a definition of a monad. And he actually states that there is no way of explaining how a monad can be altered or changed. So 300 years earlier, he predicted that today we would have such a problem with explaining monads. He didn't know about burritos. So if we look at the history of computer science, the history of programming, functional programming. Oh, perhaps, okay, was the mic not working? It was working, but a bit too far. All right, you can hear me now? Good, okay. So the history of functional programming is really a load of interrelated people. It's developments on developments on developments. And if we are to draw all of these out, we get a structure which was first conceptualized by Leibniz himself. We get a graph. Now this is a graph of influence. It shows how somebody influenced somebody else. It's directed because influence works one way. And it's also acyclic because if someone builds on somebody else's idea, they can't then build on that same idea to get the idea that they started with. But it's a very small graph, this one here. There are less than 10 people. These aren't even perhaps the most influential people in the history of computer science. We've heard of a load more in all of the talks that I've attended today. And it would be great to try and put them on here, but I only have a page with, which fits less than 10 people. In order to make a much bigger graph, I would need a computer. So our goal for today is to code a directed acyclic graph. And the way that we're going to do that is, first of all, establish a mathematical foundation for what a directed acyclic graph is. We're going to take that mathematical foundation and try and implement it. We will encounter the region of abysmal pain. And hopefully we'll escape that region with dependent types. And at the end, we'll be enlightened. Okay, so we want a mathematical definition of what a graph is. And if we abstract away from the picture that I had earlier, if we remove all the photos, what we end up with is a set of points, vertices, and a load of links between those points, edges. So one definition of a graph that I might have is a set of vertices and a set of edges. And an edge is an ordered pair of vertices. So an edge itself is a set of a vertex from that set of vertices and another vertex from that set of vertices. And this definition here doesn't rely on any code whatsoever. It's purely mathematical. I can take it. I don't even need a programming language. I can give it to somebody, and with a pen and paper, they can figure out how to write algorithms on a graph. Okay, so my first question to you guys, is this definition enough to describe a directed acyclic graph, do you think? Yeah, I'm getting some shakes. Yeah, it's not. And that's because there are some graphs I can produce with this which are cyclic. I can, for example, create an edge for a vertex to itself. Or I can create a graph which has an edge from a vertex to its parent and its parent back to itself. Those are cyclic graphs. So with this structure alone, I'm representing a lot more than what I want. Now, naively, I could take this, and I could go and code it up just using a data type for a set, right? And in fact, if you go and look at a lot of very naive graph libraries, that's what they'll do. But they end up with this problem of creating or representing more graphs than they actually need. And we can avoid that problem by coming up with a different mathematical definition. So this is the definition which I'm going to go with for this talk. It's an inductive one. So it defines how we build a graph. Either our graph is empty, in which case there are no vertices and no edges, or our graph can be based on another graph. So assuming that we have some graph n which is valid, we can create some other graph, n plus 1, just by using that valid graph and adding on a vertex. And the way that we make sure that this n plus 1 graph is valid is by saying that when we add a vertex, we have to link it to all of its parent elements, and those parent vertices have to be in the previous graph. Okay? So I start off with an empty graph, I add some vertices on, and when I add those vertices, all the links to their parents have to be in the graph. So this definition, do we think this one would work? Yeah, so I'm not going to prove it quite yet, but we can say that using this definition, it's going to be pretty hard to represent a graph which is not acyclic. In fact, it's impossible to represent a graph which is not acyclic. And the great thing about that is that any implementations that I create based on this definition, as long as they satisfy it, I can use all proofs for directed acyclic graphs on that implementation. For example, I know if I have a directed acyclic graph and I look for all the ancestors of a vertex, I know that a query for all the ancestors will always terminate. And I can prove that mathematically. So if I make sure that my implementation fits this definition, I can make sure that all the proofs for that definition carry over to the implementation. And that would be really cool if we could do that, right? So let's try and code up this graph. So for my implementation, I'm going to need a few things. I'm going to need an actual data type to implement this. I'm going to need a few functions to construct this graph, empty and add. And I'll also need to use this graph somehow, so I'll need functions for traversing it. And those functions are parents, to get all the parent elements of a vertex, and children, to get all the child elements. Child vertices, I should say. Okay, now the language that I'm sneaking in to code this up is Idris. Now, Idris, a few years ago anyway, it was a pretty esoteric language. I think it's been picking up. How many people here have coded in Idris? Oh, this is awesome. Oh, I'm so happy. Okay, how many people haven't coded but have kind of heard of it and want to play with it? Oh, that's great. Okay, I don't need to convince any of you then. Okay, so I'll do a quick run through of Idris syntax, but very quick, since I think you guys will be able to get the gist of it. Idris is a typed functional programming language. It's very similar to Haskell in terms of syntax, but it has some extra features. It's got a feature known as dependent types, which allow you to do really interesting things. Okay, so the basic features that it has, it's got values. Here I have a name, which is a value of type string, and that name is Turing. It has data types as well. You can define your data types in Idris. This is a definition of the data type bool, which has two constructors, true and false. And this is just a Boolean value, is mathematician is true. It also has functions, as you'd expect, right? So here we have a function and, which just takes two Booleans and returns a Boolean. I can pattern match on the arguments, and in fact, in Idris, this is pretty much always how you write functions. So if I pattern match on the 2 billions, I pattern match on true, I return true. I don't need to care about what's in the patterns as well, so if you see an underscore in this talk, that means we don't care. In any other case, it's always false. Idris also has type constructors. You may call them higher kind of types, such as lists. So this is the definition of a list. A list is a type constructor which takes in a type and returns a type. Okay? So list itself isn't a type, but list of string and list of ints, those are types. It has two value constructors, nil and cons. Nil creates the empty list, and cons takes a value and a list and returns another list. Okay? So we have politicians here. We don't have any politicians, actually, so that's an empty list. But we do have mathematicians. We have Church and Turing. It's a list of string. And in Idris, you also have quite a concise list syntax here. So I've got a few years, which are inside these square brackets. If you see that, that's also a list. There are a few other features that you might see in this talk, such as type classes. A really interesting thing as well in Idris is this question mark here, which is a hole. And if you have a hole in Idris, you can basically just tell the compiler, compile this code anyway, and give me some more information about what this thing might be. Holes are actually a useful feature which are now being ported to other languages. I know they're present in Scala. You can use them there. I'm not sure if they're present in Haskell. Okay, let's try and implement our graph in Idris. And for the moment, let's not use any of the advanced typing features. So our graph is a data type. I'm abstracting over whatever it can contain. So it's going to be parameterized on some other type A. That means I can have a graph of int, a graph of string, a graph of anything I want. I want to try and mirror my mathematical definition as best I can. So I'm trying to mirror my base case and my n+1 case, my inductive case. G_nil is my base case. That creates an empty graph. G_cons is my inductive case. That takes in a graph. It takes in a list of parents and a vertex and returns another graph. My construction functions are pretty much mirroring those G_nil and G_cons. So to construct an empty graph, I call G_nil. And to add an element to a graph, I call G_cons. Let's see how this might work. If I wanted to make that graph of mathematicians I saw earlier, I'd start out with the empty graph. I add one node Leibniz, and then I add another Frege, whose parent is Leibniz, and then Gödel, whose parent is Leibniz, and so on and so forth, until I get this graph, which is the graph which you saw in the beginning. Well, that's construction. It seems to work well, and it's got quite a nice syntax. Now we need to work on traversal. So for traversing my graph, I need two functions. I need a function for parents and a function for children. Let's try and work on a function for getting the parents of a vertex. Okay, so my parents function, given a graph and a vertex, should return a list of all the parents of that vertex, right? In order to write this function, I need to deconstruct this graph. So first I'll pattern match on this graph, and it has two value constructors, cons and nil. In my cons case, I want to check if the vertex that's in my graph matches the vertex that I'm searching for. And if it does, then I found its parents. Its parents are just the parents that are stored there. But if it's not that vertex, I want to look in the rest of the graph. I want to go and look in the tail. So if the vertex doesn't match, I just go and look in the tail. But what if I reach the end and my graph is empty? So if I have an empty graph and I ask for the parents of a particular vertex, well, that vertex isn't in the graph. Now, there are only two things I can return here. I could be really nasty to my users and just return an empty list. And that would be really annoying for everybody using this graph, because they wouldn't know if, for example, a vertex didn't have any parents, or if the vertex wasn't even there. And I'm a nice person, so I'm not going to do that. The only other thing I can do is return a maybe. A maybe represents a value that might be there and might not. In the case that my vertex is in the graph, I know that that value is there. So I can say, well, I can return just the parents. But if I reach the end of the graph and I haven't found that vertex yet, I return nothing. And that's because I don't have any parents to return. So this distinguishes between the case where a vertex is in there and it doesn't have any parents, and a vertex isn't in there at all. Okay, so I can use this parents maybe function now on mathematicians and Turing, and I get what I expect, Russell and Church. And if I ask for someone else, let's say Churchill, I get nothing. I'm going to need to do the same thing for my children. So my signature for my children is also has a maybe in at the end. I take a graph, I take a vertex, and I return a maybe of the list of children. Now, children is a little bit more complicated because I need to go through my graph and find out if a vertex is present in the parents, list of parents for a vertex. But ultimately, it's pretty similar logic. So we recurse, and if we find a vertex, if we traverse our list and we find a vertex, we know that that vertex is present in the list, so we can return just of an empty list. If not, then we reach the end of our list, and we know that our vertex isn't present. We can return nothing. So with parents and children, I have some traversal functions, and I can start using this graph. So I can start asking the question of what are the ancestors of Russell? And to do that, I need to write a function ancestors. Now, ancestors will take the graph, it will take a particular vertex and find out all the ancestors of that vertex. And the way that it needs to do that is by asking for the parents of that vertex, and then for each of those parents, asking for the ancestors of those parents. And because my parents function returned a maybe, this thing also needs to return a maybe. And I have a lot of extra plumbing in here, such as traverse, pure, and join. These are all things that I use to deal with monads, which we need to do because we have both maybe and list. So if I now ask for the ancestors of Russell, I get a just of Whitehead, Frege, and Leibniz. We're all looking good so far. But there's something worrying about this implementation. So I noticed that Whitehead and Russell co-authored a book called The Principia. And if they co-authored a book, that probably means that they influenced each other. So if previously I had Russell influencing Whitehead, but Whitehead, maybe he was also influenced by Russell. So maybe those two were influencing each other. If I take this graph of mathematicians and try and find the ancestors of Russell, what do you think happens? Well, I'm going to go and search here, find Russell and find Russell's parents, and that's Whitehead. And then I'll find Whitehead and find Whitehead's parents, that's Russell. And then I'll go and find Russell's parents, and that's Whitehead. And I'll end up infinitely recursing. But hang on a minute, I said that for a directed acyclic graph, if I'm looking for the ancestors of a node, I should always terminate. So something's gone wrong here. What's gone wrong is the fact that I shouldn't have been able to build this graph in the first place. I should not have been able to add my vertex Whitehead, which referenced a parent Russell, which wasn't present in my graph. Now, Idris is one of the really cool features of Idris is that it will tell you this. You can ask it to check for totality. And what that means is to check for whether a program or a function that you write is defined on all inputs and whether it will terminate. And in fact, if I ask Idris, for this ancestors function, is this total? It'll say, no, it's not. You've written something which may not terminate. The way to solve this problem is, in a similar way to solving the other ones, is to add a maybe. When I now add something to the graph, I need to first check if all of the parent elements are present in the graph. So I can only add a vertex to a graph if all of its parents are contained in that graph. Otherwise, I can't, and I need to return nothing. So we have a problem here because we've written this data type for a graph. We've tried to mirror our mathematical implementation. But we've ended up with loads of partial functions. And anytime anybody uses this graph, they're also going to write partial functions. This is a problem which doesn't just plague graphs. It, in fact, plagues almost any collection you can think of. Whenever you ask for an element, then that collection needs to check whether that element is there or not. And if that element isn't there, it really should be returning you a maybe. But this isn't that nice, because for this particular graph, I know that Turing is present in there. I've added Turing into the graph just here, and now I'm asking for the parents of Turing. I know Turing is present in the graph. So I know that this Turing influences value here is always going to be a just. There is always going to be a value in there. Nevertheless, in my code, I need to cater for this case where it's nothing. And that's not great. It means that as a user of this, I'm writing a lot of dead code, because I'm writing lots of cases which deal with a value that isn't there. Another concern, which is perhaps slightly bigger, is that in coming along and developing this implementation, I encountered a bug, the bug of infinite recursion, and that was something that I could only find through later testing, after using the API. Now, I've encountered this problem quite a bit in quite a few collections frameworks, quite a few different areas, and it turns out that there's a name for it. It is known as the region of abysmal pain. So if you consider the set of all programs, in a typed language, there'll be the set of programs that type check and the set of programs that work. And really, everything we write should be somewhere in the middle, in this orange region, because we want to write code that works and that types checks. But sometimes we end up writing code that type checks and doesn't work, actually quite a lot of the time. That's why we have tests in the first place. Our infinite recursion bug, that was code, it type checked, but it didn't work. And occasionally, especially with collections frameworks, we want to write code which works because we know it works, but it doesn't type check. And that's the region of abysmal pain. But I think that we can escape this region. In order to do so, we need a more advanced type system. But first, let's go on a bit of a digression and think a little bit about the nature of types and what they actually are. So there are many definitions of a type. The one that I'm going to use today is to think of a type as the set of values that it represents. For example, the type bool has two values, true and false. The type string has many more values. It's got Turing, Churchill, it's got foo, the empty string, loads and loads of other values. You can think of some other interesting types as well. For example, the type unit has a single value. The type void in Idris has no values at all. But what do types and values mean in the context of our graph? Let's try and think a little bit about what type or what set of values we want our parents to be. For this particular graph, I start out with the empty graph, and I add Leibniz. The only thing that my parents can be is the empty list, because there are no elements in this list or in this graph already. If I then add another vertex to the graph, Frege, Frege's possible parents could be none, the empty list, or it could be Leibniz. So the set of values now is slightly bigger. What about my next element? If I add Gödel into the graph, well, it can now be empty or Leibniz, or even Frege, or Frege and Leibniz, or Leibniz and Frege. So the set of values now is even bigger. In fact, the set of values that we want our parents to take is dependent on the members of our graph. But our add function doesn't reflect that. Our add function just says that parents are a list of A. Really, what we want to say is that our parents are a list of members of our graph. In other words, we want to say that parents are dependent on the value of the graph. Now, it turns out that in a language like Idris, you can do this, because Idris has a feature called dependent types. And dependent types are ways of computing types based on values. Here I have a function, isSingleton, which takes in a value of type Boolean and returns a type. If that value is true, it will return an int, and if that value is false, it returns a list of int. I can then write another function, makeSingle, which takes in some Boolean and returns something of type isSingleton. If I take in true, I need to return an int. I return 0. If I take in false, I return empty list. Okay, so that's a really cool feature, but how does that help us solve our problem? Well, we can make our graph dependent on the members that it contains. My graph now takes in a list of members. Members are a value, a list of type A. In my nil case, my graph has no members, so it's parameterized by the empty list. But in my cons case, my graph has the members of its tail plus the vertex that I'm adding, v, consed on top of that. So the type of gcons is a graph of v cons m's. And my parents need to be a list which are somehow members of that of my tail. This is what that might look like. For the empty graph, it's just gnil. Let's say that I have a graph of mathematicians Frege and Leibniz. I have an empty graph, I add Leibniz and then add Frege. That has the type graph Frege Leibniz. So this graph is dependent on the value Frege Leibniz. I could also construct another graph of that same type. In fact, these are the only two values corresponding to that type, where Frege doesn't have Leibniz as a parent. But if I try and assign a value, such as the empty graph, to this graph type, Frege Leibniz, I get an error. And that's because I cannot construct the empty graph, or I cannot make the empty graph construct this particular graph with gnil. Well, that's kind of cool, but how does that help us test for membership? Well, some value x is a member of a list of members if two things are true. It's either a member if it's at the head, so if it matches x cons x's, or if it's somewhere in the tail. So if members matches something else, y cons x's, where x is a member of x's, then x is also a member of y cons x's. And I can use dependent types to code this up. I'm going to create a data type lm, which takes in a value x of type A, a value x's of type list A, and I can only construct this if x is in x's. The way that I do that is that I define two value constructors here and there. If the element is at the head of my list, then it's here. If it's not at the head, but I know that it's somewhere later in the tail, then I can define an element of x with y cons x's. So I can define an element on a different list, y cons x's, provided that I know that x is somewhere in the tail. Well, what do the values of this look like? Let's say that I want to show that Turing is an element of the list Turing, Church, and Russell. Well, the only value of lm that will satisfy this top type is here. So Turing is here. Let's say that I have some other value, Churchill. I want to say that Churchill is a member of Turing, Church, and Russell. Well, Churchill isn't. So if I try and assign the value here to this type, then I get an error, because here has to correspond to the type of the element that is at the head of the list. Now, a different person, Russell, is in this list. He's at the end of the list, and I can construct an isElement for Russell using there, and here. But if I instead try and say, well, what if I try and say Russell is at the head of this list? Well, he's not, so if I try and say that Russell is here, I will get a type error. And one of the really cool things I realized about this is that the existence of this value of type lm implies that that element is a membership of the list. So by having a value of this type, I am proving membership. Is there a way with this lm type that I've created for me to find if x, some arbitrary x, is a member of a list of x's? So I'm going to create a data type, member of, which takes in some value x and a proof that x is an element of some list of members and returns a member of those members. And this is useful because I can then take this proof and put it in a list. In Idris, this is known as a dependent pair. There's actually some special syntax for this, so you don't need to write it each time you want to use one. So now when I want to construct a list, if I want to construct an empty graph, I can just call gnil. And if I want to add an element onto a graph in a similar way to before, I just call gcons. But this time, I'm now parameterizing my graph. So if I take in a graph with members m's and add a vertex v, I get a graph of v cons m's. Now this is what that might look like. It's a bit more verbose now because I have to add in the proofs whenever I add a list of parents that those parents are members of the graph before. It turns out that Idris can infer a lot of this for you, so you don't usually need to write the proofs out like this. Okay, so if I have some member, is there now a way for me to use this proof that that member is a member of my graph to write a parents function which does not need to be partial? And there should be, right? The way that I do this in Idris is that I would pattern match first on my proof, on member. And if I pattern match on the proof itself, either the member is here, it's at the head, or it's later. Now the interesting thing, if it's here and I pattern match on my graph, the only value of my graph that will satisfy this pattern is gcons. I don't even need to cater for the case when the graph is nil. And that's because if I have a member of a graph, my graph cannot be nil. The other interesting thing is that if I have a member of some value, and I know that it's here, I know that it's at the head of my graph. So this pattern x in gcons is the same as the x in member of. I've proved that my value x is at the head of this list. And in fact, if I were to try and write anything else there, if I were to try and write gcons y, I would get a type error. What if it's later? Well, if I have a value which is later, I know that it can't be at the head. So I have a different constructor, gcons y. Similarly, I don't need to cater for the nil case. And that means that I can now write a function which will just get me the parents of this member. I don't need to cater for the case where my list is empty because I know that I'll never reach it, and I've proved that to the compiler. And the way that I do that is that I just get all the members of the parents, and if the parents are in the tail, I go and look, given their proof that that member is later, I go and look for the parents in the tail. And this function is total. Idris will tell me that. And the way that it knows that is each time I call it recursively, I'm calling it on the tail. And so if I have a recursive data structure and I keep calling it tail and tail and tail, I can prove that it will eventually terminate. I can do the same with my children. You don't need to look at the definition too much, but notice that I don't need to return a partial function, and I don't need to cater for my nil cases. Let me try and write a function for getting the ancestors of an element now. So if I have a graph, and I have a member of that graph, and a proof that it's a member, I should be able to get a list of all the ancestors now, shouldn't I? Well, first I need to look for all the parents, and then I need to get the ancestors of all those parents. But I have a problem, because in order to get the ancestors of those parents, I need a proof that those parents are in the graph. And I haven't got that here. And the way that I can get that is by editing my parents function. I can, instead of returning parents as a list of A, I now need to return a list of proofs that those parents are in the graph. So I return a list of member ofs. I can then use that when writing my ancestors function. So I can now use the member of that I got before, that's now P's, and just pass that into my ancestors function again. So I can reuse the proofs that I spit out before in my next call. And that's really cool. So I now have no partial functions. I've implemented this. It's very similar to the initial mathematical definition I have. I've just carried all the proofs across. It's quite similar to my mathematical definition. So for my empty case, it's pretty much the same. And for my inductive case also, I've said my add function is basically constructing a gn plus 1. Well, what about termination? Does this always terminate? My ancestors function now. I can only ever construct valid directed acyclic graphs. So it always terminates, right? But if I ask Idris whether this thing terminates, Idris will say that it doesn't know. Why might that be? Well, the reason is that in order to prove termination, to prove totality, you need to deconstruct something and step down it each time. Before, I knew my parents' function was total because I stepped down each time and looked at the tail each time. But in this case, I'm still just looking at the graph. I shouldn't need to, though. I should be able to step into the tail. It turns out that our parents' function that we wrote didn't completely mirror our mathematical definition. The thing that we missed out was that we said that for any given graph before, the parents were members of that graph. But actually, the parents aren't members of that graph. They're members of the tail of the graph, because a vertex can't be its own parent. So we can rewrite our parents' function now to say that the graph we take in must be non-empty, it must be n consems, and the list of member of proofs that we return must be part of m's. So that proof must be part of our tail. We can then use that to write a different definition of ancestors in which we now look at the tail each time when we're searching for parents. So I get my parents, and when I now look for the ancestors of those parents, I only look in the tail of the graph. And if I ask Idris if this is total, it will be able to say, yes, this is. Which means that we've been able to prove termination true as well. And so at the end of this, I hope that we now have a slightly smaller region of abysmal pain. We've managed to make our code type check that previously didn't. We've managed to eliminate the bugs that we had with infinite recursion. So the code that previously type checked but didn't work, we've written less of that too. And I think that languages like Idris kind of help us move these circles together. Now, if you want some more ideas of how to play around with graphs, there are a few other really interesting ones in Haskell. There is a paper called Alga and a repository based on it with a different way of constructing graphs. It constructs them through composition. There are a few other really interesting GitHub repos that I've found, such as Dagmore, which uses similar ideas to construct directed acyclic graphs in Haskell. And I strongly, strongly urge you, if you haven't already, to go and check out Idris and take a look and play around with dependent types. There's also Idris 2 coming around the corner. Thank you very much.